Work turned in. If you were behind, there's a few people that's been behind in here, and so I know a lot of work was turned in here. Some of you got some stuff turned in. That's great. So we are. Let's see, where are we at? We have this week, we have next week, and then we have finals. That's it. We are almost done with the semester. So if you've got stuff that you're missing, uh, not much time to get it turned in. So okay, the final for this class. Finals week. Finals week is 2 weeks from now, and finals are Wednesday, Thursday, and Friday for all the classes. So we'll meet on Tuesday and probably review. Anyone not sure if they're exempt or not. This is a class that you do not have to take the final if you meet all the exemption requirements. Yay! Algebra 2, Geometry, Algebra 1, they all have to take the winter final. Algebra 3, it's optional. So if you meet the requirements. Of course, if you don't meet the exemption requirements, it's mandatory for you and it will count in your grade. If you are exempt, you can choose to take the final if you're trying to bump your grade up a little bit, right? Maybe you got a 78 and a half or 88 and a half. You're trying to get to the next grade. If you are exempt, you can take the final, and if you do great and it raises your grade, I'll put that final grade in there and you'll go yippee. If you take the final and you totally bomb it because, oh, I forgot we did that back in October and September, then I'll just throw it out like you never took it and say, well, I don't remember I'm taking the final. That never happened at all. So you'll keep your 88 and a half or whatever you got. But that's only if you're exempt. If you're not exempt, you have to take the final. So remember, exemptions are, first of all, no more than 4 absences or tardies in 6th period. Advisory. If you're absent more than 4 times in advisory, you can't exempt any final. You got to take all your classes finals. So that's the big one. You don't want to miss advisory. But other than that, if you've got that covered, no more than 4 absences or 4 tardies in my class, in there in 5th period. No missing assignments, including practice assignments, which means those practice tests. If you haven't taken practice test, go take it. It doesn't count towards your grade, but it counts as a missing assignment. And then the other thing is your grade has to be at least 75%. So if your grade's less than 75, you might want to go back. If you've got everything turned in and your grade's below 75, you might want to go back and redo some of the lower assignments to get your grade up before finals week. So that's the big thing. Oh, and no fees or fines, but we don't have fees in this class. So I don't have to worry about that one as far as an exemption. But there's not a whole lot of people that are missing much. So most of you are in really good. Um, oh, here's Mr. Price is looking for the exemptions requirements. I just listed them. I don't have time to tell him Mr. Price, but I'm sure somebody has sent them to him. But yeah, the exemption requirements: tardies, absences, missing assignments, grade is 70%. Oh, there you go. Miss Pinion is going to send him the exemption requirements. So Mr. Price can take care of. All right. So gone over this schedule. The other thing I need to tell you is next week I will not be here during this class. I'm going to be on an airplane coming back here during this class, but I will not be here. So I will have a video for you next week to watch. I think we only got one lesson next week. It's a short week, easy. I'll have a video for next week's lesson. I'll pull it from past Mr. Brock because Mr. Brock's done that lesson many times in the past. I'll go back and my videos and find next week's lesson and let Mr. Brock from years ago cover that for us next week. But I will have that for you next week. So watch that video. Make sure you get next week's assignment done because you don't want to have the last week being the missing assignment that makes you take the final. So we'll get there, but we will meet the week of finals on that Tuesday because the finals are Wednesday, Thursday, and Friday. The finals for this class, by the way, if you end up having to take the final, is on Thursday. Thursday at 9:15. So a little bit later than our normal starting time. I may open up the meet early just in case someone forgets so they don't freak out. What? Where's everybody else supposed to be taking the final? Yeah, no, it's 9:15 and you got like an hour and 55 minutes. It goes to like 11:10. I don't expect anyone needs an hour and 55 minutes to take the final in this class. It won't be that long a final if you need to take it. But that will be 9:15 on the Thursday of finals week, December 18th. So almost there, guys. Almost there. Just gotta hang on a little bit longer. All right, let's see where we're at for Algebra 3 this week. Go to our grade screen as usual to check in. I see no missing assignments. We are down to 4.04, solve exponential equations with unequal bases. Ah, yes, we've got to review a little bit that we were looking at exponential and logarithmic functions before Thanksgiving and the properties of logs. This week we have 2 lessons, graphing exponential. So we'll do that along with solving. Those kind of go hand in hand. And then next week, graphing log functions will be the video I'll have for you to cover next week on that. And that should be pretty simple too, because we'll use Desmos. Use Desmos on that. So solving exponential 4.04 and 4.06. Switch over there. Solving exponential. All right. So I guess before we look at unequal bases, we should review real quick. Let's see. I pulled these notes out that I found from before Thanksgiving. Not focusing. Focus. That's a little better. All right. Remember if we had like 1 over 256 equals 16 to the x minus 9th, what our goal was is to get 1 over 16 squared, 16, get the same base. If we could get them both to the same base, 16 to the negative 2 power equals 16 to the x minus 9 power, that allowed us to just drop the bases and set the exponents equal to each other. Negative 2 equals x minus 9. And then we could make it easy to solve. X equals 7. So if we put 7 up here, 1 over 256 equals 16 to the negative 2 power, and solve that. If we could take 1 over 4 to the 4th equals 4 squared x minus 9. If we get them both to base 4, then we can set the exponents equal to each other and solve that way. We had square root of 11 and 121. We got them both to base 11. 11 to the 1/2, 11 squared. We were able to get down and solve that. So it was all about getting the same base. But what happens if they're not the same? And we can't just do that. So uses of logarithms with different bases. So when you turn 16, you decide to put $50 in a savings account so that you can put $2,500 down payment on a new car when you turn 18. If the account has an interest rate of 3% per year, compounded monthly, how long is it going to take you to get $2,500? Well, you make it by your 18th birthday. So $50, it's going to take a while for it to turn into $2,500. The formula representing compound interest is A equals P for principal, 1 plus the interest rate divided by the number of times a year you get it, all raised to the power of number of times in years. So A is the amount of money in the account after T years. P is the principal invested. R is the interest rate that we got to put in a decimal format, not a percentage format. And N is the number of times the interest is earned or compounded on the account per year. So when you substitute numbers into there, $50, 3%, 12 times a year, and we end up with the equation 50 equals 1.0025 to the 12t. But trying to solve that, this is an exponent. These do not have the same base. How would we solve that? We can get it down. We don't know how many years it'll take. We're trying to solve for t. And we know we can solve for a variable in the exponent, but we have to have the same base to do that. So that's the problem we're running into. How do we do the same to solve for this when we don't have the same base? We can't turn 1.025 and 50 into the same base. Those are Very different. So we're going to learn how can exponential equations with unequal bases be solved, and how do the various parts of an exponential equation affect the entire equation. So this is a little review here where we said if we had 2 to the x equals 8, we could make 8 2 to the third power. So they have the same base. 2 to the x equals 2 to the third. And so x equals 3, because we just set the exponents equal to each other. We could also solve this using the equality property and the power property of logarithms. So let's see what else they're doing with that. Okay. So they're taking, let's write this down. Let's start making some notes here. If we have 2 to the x equals 8, we know we can make this 2 to the third and solve it that way. But let's pretend that we can't make these the same base. So what they're doing is they're saying the equality property says that if log, let's go back to the equality property, log b of x equals log b of y, then x equals y. That makes sense. If these are the same base, then if the log of this base of x equals the log of this base of y, x has to equal y. So using that property, they said, okay, what if we took the log of 2 to the x and set it equal to the log of 8? Right? Log of 2 to the x equals log of 8. So then we can apply the power property of logarithms. Remember, the power property of logarithms says if we have an exponent, we can move it out front, and this rewrites as x times log of 2 equals log of 8. Let's see, do I have those? Just trying to pull out some notes on that. Oh, there it is, the power property. We did this in our notes. Like if you have a coefficient out front, you can move it and make it the exponent of the argument, which means you can go the other direction as well. If you have x to the y, you can move it out front and make it a coefficient. So 4 log 7 to the third is the same as log 7 of 3 to the fourth power, or 81 in this case. But so you can go back and forth either way because these are equivalent to each other. So that's what's saying here that x log 2 would equal x log 8. In this case, if we're solving for x, that means we can divide both sides by log 2. So x would equal log of 8 divided by log of 2. So that's a way to do that. We have 2 different bases that we know we could have made them the same base. So this is just a good one to play with. Let's get our calculator out and say, okay, if we have log 8 and we divide it by log 2, it equals 3. We know that's the answer. 2 to the third is 8. 2 to the third is 8. So that is another way we can do that. Log 8, x log 2 equals log 8. So we can divide those and get x equals 3. And they went ahead and left them on the same side first before dividing it over. So let's look at some more examples. Solve 4 to the x power equals 7 to the x plus 1 power. So they're doing all 3 steps here as separate videos. And it says round the solution to the nearest hundred. So let's go through these videos and then we'll do examples on paper. Rewrite as a log equation. So the first thing we have to do, let me switch over to video mode here.
Using the equality property, write each base as the argument of a logarithmic equation. Using the power property of logarithms, turn each exponent into a coefficient on the logarithmic expressions.
Okay, that was step one. Let's look at step two. Now that we've rewritten them as logarithms and using the power property to move the coefficient to the front.
Solve for the variable. First, use your calculator to find the decimal equivalent of each logarithmic factor. Find the approximate value of log of 4 and the approximate value of log of 7. Distribute each decimal value to the factor which precedes it. Combine like terms. Divide. Round to the nearest hundredth.
So it becomes just a basic algebra problem at that point. It's just not using integers, it's using these long decimals. But it's basically like 0.6x equals 0.8x plus 0.8, and then you just have to divide and get it down to what does x equal. Step three, check your work.
Substitute the value of the variable into the original equation. The solution is confirmed.
Yeah, you did that with a calculator. 4 raised to the power of negative 3.48 is 0.008, and 7 raised to the power of negative 2.48 equals 0.008. So you got to use a calculator a lot with these equations here. So let's revisit this earlier problem. So we can put this in our notes to kind of get with what they were working on. So they used A equals P 1 plus R and T. So let's kind of get caught up with what they were doing on that. So we did their problem with the wanting to know how long it take to get $2,500. If we put in $50 at 3% interest, we get 12 times monthly, 12 times a year. So we took the 1.03 divided by 12, made that 1.0025 because that's what 0.03 divided by 12 is. Then we divided both sides by 50 because this is 50 times this. And that got it down to what they had on page 1. 50, which is 50 to the first power, equals 1.0025 to the 12t power. So according to our equality property, if the log of x equals the log of y, then x has to equal y. Well, since x equals y, it already said x equals y, we're going backwards and saying, then this must be true. The log of 50 has to equal the log of 1.0025 to 12t. So we just set each of those as a logarithm. The power property says we could take this 12t and move it out front, make it a coefficient. And now we're just punching this into our calculator to see log 50 equals 1.698970. I went 6 digits. And over here we got 12t times, and we're going to see what the log of 1.0025 is. So let's see. 1.0025, the log of that is point, let's see, let's go 6 digits on this as well. 001084. So we would multiply that times 12t. So we'll go ahead and just, since I got it on the screen, we'll just go ahead and multiply it by 12 right there. So this would be 1.698970 equals 0.013, and it would round up 0.013t. So we took 12t times that, we get this many t. So all that's left now is divide both sides by the 0.013013. So t will equal, this is how many years it's going to take that $50 to grow to be $2,500. So we know we can have that down payment for a car. 16 years old, hoping to have this by the time they're 18. So hopefully this is 2 years or less. What are the odds? Well, the odds are somebody's not good at math if they think they can get that in 2 years. So 1, 6, 8, 6, 9, 8, 9, 70 divided by 0.013013. Oh, looks like it's going to be about 130.56 years if we round it to the nearest hundred. So by the time they're 146, they'll have enough for that down payment. $50 is not going to get them there anytime quickly. It'll take 130 years. I don't think that's going to meet the timeline they were hoping for. Oh, there it is, a 130. And they got 5.637 just because they went different amount of decimals on that. But okay, here's an exponential equation where identical bases do not exist and cannot be made. Yeah. How about this example? E to the 2x equals 30. All right, let's try that one. So this one, if we want to use our logarithmic equality property, we should use base E, right? So use natural log e to the 2x equals natural log. This was using base 10. This is using base e. It doesn't matter as long as we use the same thing on both sides. Move this out front. 2x ln of e equals ln of 30. Again, that power property. And what is the ln of e? Oh, this, I like this. Where's that calculator again? Clear. ln of e. So here's e, and we'll take the natural log of that. It's 1 because it's like taking what's the e to what power equals e. So this is 2x times 1 equals the natural log of 30. What is the natural log of 30? It is 3.401197, going 6 digits. So this is just 2x equals that, so just divide both sides by 2. And it said nearest thousandth. Is that what it said? Let's go back and look and see. Or nearest hundredth. Nearest hundredth. So pull our calculator back up. That'd be 1.70. X equals 1.70. Because we got 2 zeros in a row there. Let's see how they work. Log of base e is called natural log. Natural log and e cancel each other out. So you got 2x equals natural log of 30. 2x equals 3.4012 divided by 2, 1.7. Okay, so now it's time to try some on your own. With exponential equations like a equals p1 plus rt, where there's a number of parts that can affect the entire equation, understand how each part works will help when you need to create an exponential equation to model it. So a is the amount after the exponential growth or decay has occurred, right? P is the principal. That means the amount you start with at the very beginning, like the amount of money you put into an account, the population of bacteria before it starts growing, or the amount of an isotope before it starts decaying. That's what P is. 1 plus R. R is the rate of change. Is it growing or is it decaying? If it's going to increase by 3%, then it's 0.03. If it decreases 3%, then it's negative 0.03. So if 1 plus R is greater than 1, your principal is growing. If 1 plus R is less than 1, it's decaying. And if r equals 0, it's a linear equation, right? If there's no growth or no decay at all, it's just a straight linear. And t is the amount of times the growth has occurred. So if a fly population doubles every year and you want to know 10 years, then t equals 10. So it also talks about changing time increments. Because if we've been saying it's for every year, we want to say instead of for every year, I want to know for every month or something like that. So they said the lizard population starts at 14 and doubles every year. But now we need to find the population each month because it's growing so big. We need to know how many new containers they need every month or something. So there are 12 months of the year. So let's see how that wraps into this function. So let me see. Let me write down the lizard function here. So how does that wrap into the function? So if we want to say what happens every month, means we would have to take the lizards and say we started with 14 and now we need 1/12 of that 12 times a year. 2 to the 1/12. So 1/12 to the 12. Remember, if we have power to a power, 2 to the 1/12 multiplied times 12, you multiply those together, and 12 over 12 is 1. So we have not changed the equation. It's still the same equation as this. We've just rewritten it in a different form where we put this 1/12 power inside here so that we can calculate per month. If we're going to take 1/12 of the growth, we need to take it 12 times in order to still have the same equation. 1/12 to the 12. And that's what they're showing right here. 2 to the 1/12. But now you're taking it 12 times a year instead of just once. So then they break it out. What is 2 to the 1/12? Well, that's the 12th root of 2, which is 1.059. That's how much it is on a monthly basis. So they write that. I'll put it on here. 1.059 simplified per month. So this is the growth of lizards per month. 1.059 12 times in a year. So we started out saying it doubles every year, which means each month we can use this equation to find out after 3 months or after 7 months or something before a year. We can just do 1/12 to the 12th. What if we wanted weekly instead of a year? Yes, we would do 1 over 52 and 52t, right? So if we wanted weekly, 1 over 52, 52t weekly. And we can simplify that by taking 2 to the 1/52nd power, which would be the 52nd root of 2. But we can convert it to whichever we want to be there. So there's the 14 to 1.05912t. It's simplified. So it says 5.9% is the rate of growth in 1 month for the lizard population doubles every year because this is 0.059 larger than 1. And they want proof it's the same thing. So it's like, okay, if t equals 1 both ways, 14 to the 1.05912t, if t is 1, take it to the 12th power, and it'll end up 2 and double 2828. And we're already to the lesson summary. So the value of a sailboat decreases 12% every year. The sailboat's worth is calculated using this function, 50,000 to the 0.88t, which is 1 minus 12%. That's where the 0.88 comes in, right? Find the rate of decay each week. So let's see if we can do that before we look at the lesson summary. Let me write this equation down. Okay, so this is on an annual basis. On an annual basis, it's losing 12%. We've only got 0.88 left each year. So if we want to know weekly, 50,000. 0.88 to the 152nd 52t. 152nd, again, that doesn't change what the value is. It just rewrites it. So we can take this and get a calculator and simplify it. Let's see what 88, 0.88 to 152nd. 0.88 raised to the power of parentheses 1 divided by 52 equals 0.9975. So 50,000 times 0.9975, and we'll go 6 digits. 754, and it would round up to 5 since it's just 6. So each week it's only losing like 0.0025. See, it's not losing very much each week. 12% for the whole year, but just a little bit each week. So check your work. They went with just 3 digits, 0.998. We went 997545. So about 0.2 or what we calculated 2.25. So it decreases that. So rounding it to their digits, we get the same thing. So lesson summary says, rewrite the exponential equation as a log equation to solve with unequal basis. Solve for the variable, check your work. Finding rates of growth or decay for different time intervals. You just 1 over C inside the parentheses and a C outside the parentheses. See what kind of practice problems they got for us. Pretty short lesson. Nothing wrong with that. Solve these exponential functions. Okay, this one's a nice simple one to start with. 5x equals 20. Oh, wait, that was 5 to the x, right? Not 5x. 5 to the x power equals 20. We can't make this base 5 because 20 is not a base 5 number. So we would take a logarithm. 5 to the x equals logarithm of 20. Move this out front to be x log 5 equals log 20. We can divide both by log 5. So x equals whatever the log of 20 divided by the log of 5 is. So let's get our calculator and figure out what that is. What is log 20 divided by log 5? Log 20, log 5. It's 1.86 if we round it to 2 decimals. 1.86. So 5 taken to the power of 1.86 is 20. Let's try that. 5 raised to the power of 1.86. Now, it may not be exactly 20 because I've rounded it to 2 decimals. But it's 1995.6. Yeah, so if we'd have done more decimals, we'd have got closer to 20. That looks like that would be right. Check your work. 1.86. They rounded it also to 2 decimals, just like we did. So that's right. So there are 5 practice problems there. You just take the log of each side. Activity 2. Here's one with the rate of decay. It says 40% every decade. If they want to calculate it annually, you got to do that 1/10 and 10 to figure out what it would be every decade. It'd be 5% per decade. I mean, per year, if it's 40% per decade, it would lose 5% a year. So let's look at the assignment for this. This doesn't look too bad. A car cost $20,000 when it was purchased. The value decreases 8% per year. Find the rate of decay per month and select the correct answer. So if it's 8% per year, you got to convert that to months. Do that 1/12, right? 1/12 power. Solve 4 to the 2x equals 7 to the x minus 1. So make both of those logarithms, use the power property, solve for x. There's a calculator right up here. With this calculator, if I wanted to take log 10, I hit log first. See, it puts parentheses. If I want to take log of 23 or whatever, you hit the log button first on the calculator they use here in Buzz. So that's good to know. Mine, the one I'm using on my computer, you have to put in the number first. The one in Buzz, you put the log first. So I like that. Let's see. Ashley solved this exponential equation where 3 to x plus 1 equals 15. What was the first thing she did incorrectly? So there's a problem somewhere. She messed up somewhere. First thing she did was set both sides as logarithms. That looks correct. Go through the steps after that and see where did she goof up, because somewhere something's wrong, apparently. Was it step 1, 2, 3, or 4? So somewhere in the first 4 steps, she did something incorrectly. You put $175 down to save for a $3,000 down payment. If it gets 3% a year monthly, how long does it take to earn $3,000 if you don't put any more money in there? 8 years, 96 years, 93 years, 94 years. A lot of years. That's what it sounds like. All right. Let's look at the second lesson, graphing exponential functions. And I'm going to open up Desmos because I'm sure we're going to need it if we're graphing. Oh, is it the graphing calculator loading? No, that's the Discover way. Desmos graphing calculator. There we go. Okay. Wacław Sierpiński. That's click on that, it'll tell you Sierpiński. He was a Polish mathematician, and he worked with fractals that gave us the Sierpiński triangle. So there's this really cool video about the Sierpiński triangle. So a fractal, let's talk about a fractal is. It's a geometric figure that's divided into pieces which are similar in shape. It's like a square being made up of squares, right? All the squares, they're just smaller than the original square, but they're all squares. So here is a Sierpiński triangle, which you may or may not have seen before. Sierpiński had a lot of time on his hands.
One method of creating the triangle is by first drawing an equilateral triangle. Remove another, smaller equilateral triangle from inside the original. The vertices of the removed triangle meet at the midpoints of each segment of the larger triangle. Next, 3 more
So I'll just point out that when it divided that at the midpoints, now it's created all of these other triangles that are all exactly the same size. Every one of the blue triangles are the same size, and the white one is actually the same size as the blue ones as well. But they're just focusing on the blue ones, and it's going to continue.
equilateral triangles are removed from inside each of the remaining 3 triangles.
And all the blue ones will be the exact same size and comparable to the original.
The process of removing triangles inscribed within the larger triangle can continue forever.
It can continue forever. It's just harder to see. But that is the Sierpiński triangle, which just gets smaller and smaller and smaller. So after this lesson, what does the average rate of change vary? Why does it vary on an exponential function? What effects does adding a constant have? And how can exponential functions be utilized to fit existing data? So let's look at Sierpiński's triangle. It demonstrates an application of an exponential function, oddly enough. An exponential function is a function with the variables in the exponent, and the base is a positive real number not equal to 1. So the exponential function that's represented by Sierpiński's triangle is 3 to the x power. where x is the stage at which the triangle is removed, like the first stage. The first stage, when you remove the triangle that's in the middle, f of x represents the number of triangles remaining. When you take that first step, now you have 3 to the first number of triangles. You have 3 blue triangles. The second step, when you remove the middle of all those triangles, now you have 3 squared triangles. You have 9 triangles. And it just continues in that way. So let's look at it again, having that in mind, counting the number of blue triangles as an exponential function.
The exponential function is f of x equals 3 to the x. At stage 0, when x equals 0, the function equals 1, indicating there is only one solid triangle. This is how the fractal begins. At stage 1, f of x has a value of 3. This means that the first time a triangle is removed from the center, there are 3 triangles left. At the second stage, f of x has a value of 9. So 9 triangles remain. At stage 3, f of x has a value of 27. So the third time equilateral triangles are removed, 27 triangles are left, and so on.
And so on. So you see now how Sierpinski's triangle is actually an exponential function, because each time you remove a section, it exponentially has 3 times as many triangles as it did the step before. So let's graph the exponential function using technology. So here we go. If we say y equals 3 to the x, so we can see that right there. At step 0, we have 1 triangle, 3 to the x. Then as we get up to 1, there it is, we have 3 triangles. When we get up to 2, get right on 2, there's 9 triangles. And of course, we've got to go way up here to get to step 3, when now there's, where am I? I'm way above it, 27, and so on and so forth. And you start to see it gets really steep really quickly. Not so steep here at the beginning, going from 0 to 1's not that steep, but it gets steeper and steeper and steeper the further that it goes. So they went ahead and set up their little graph. Looks a lot like ours. The domain of this function is all real numbers. That's true, because even though it's getting really steep, it will continue going towards infinity. I mean, we can find out what x of 25 is, but it's going to be a huge number. I mean, it's going to be way off our screen. We'd have to zoom out a long, long, long ways to ever find x equals 25. There's x equals 7 somewhere way up here. So it's a long ways out of there. We're not going to try to zoom out that far. But yeah, the domain goes forever. But what is the range? That's the question. What possible y's are there for this exponential equation of 3 to the x? Well, we know there's no negatives, right? This will never 3 to whatever power. If we say 3 to the negative 1 power, well, we can zoom in and see what 3 to the negative 1 power is. It's right there. It's 0.333. Negative 2 is right there. It's not a negative number. Because remember, if we have 3 to a negative number, that's the same as 1 over 3 to a positive number. So like when x is negative 2, that's the same as 1 over 3 squared. So 1/9, which we see as the 0.11, 11, 11, 11, all the ones. So as this goes towards negative infinity for the x, it says, let's move over here a little bit. It says the y is 0, but is it? Is it really 0? Let's zoom in. It's saying it's 0 here. I'm going to zoom in a ways to where we're really getting down to some good decimals. What's it say now? Oh, look, it's not 0. It's 0.0000000299. It's just such a small number that if we zoom out a ways, finally it goes, it's just 0. Because it's so small, I can't even really tell you. We zoom in even further. Well, see, now we can actually see it. It's not on the line. It's given to us in scientific notation now. It's saying that there's 8 zeros in front of that 2 with a decimal. 0.00000000. But yeah, we zoom in far enough, we can see, oh yeah, it does not equal 0. And it will never equal 0. So for this equation, there we go. Now we're back out to a decent range. Even though at some point it says 0, we know it's not. It's all y's greater than 0. That's the range. The range is all y's greater than 0. Not greater than or equal to 0, because it's never equal to 0. Because look, if x is -5, that's 1 over 3 to the 5th, which is 1 over 243. So at -5, it's 1 over 243. That's a very small number when you divide 1 by 243, but it's not 0. If x was -10, this would be 1 over 3 to the 10th. And 1 divided by 3 to the 10th is a very, very, very small number, but it's not 0. It'll never get to 0. So the range is y is greater than 0. All right. Here's a little slider we can kind of play with. If we have a base greater than 1, a base, like our base here is 3, right? A base of 3. If the base is greater than 1, this is what our graph is going to look like. The bigger the base gets, the steeper it gets faster. All right. See, is it 1.5, 2, 2.5, 3, 3.5, 4? It gets steep fast because we're raising 4 to an exponent, and it's going to go up faster than 2 to an exponent. Because it's multiplying by 4 every time you go up 1, where the other one's just multiplying by 2. But what if our base is less than 1? It's between 0 and 1. It's a decimal. So instead of 3 to the x, what if we have 0.3 to the x? Oh my goodness. It's totally opposite. It gets steeper the closer it is to 0, but it's coming down instead of going up. The closer we get to 1, if we get to 1, it's just a straight line, right? 1 raised to any power is just going to be 1. But if it's less than 1, 0.9 is not nearly as steep as 0.3. So knowing how the graph looks is important. The base affects that a lot. Move the point on slider B. When the base of an exponential function is greater than 1, describe the graph. Well, the larger the base, the steeper it goes up to the right. To the left, it's going down close to 0. There's a horizontal asymptote at 0. Uncheck greater than 1, check the one between 0 and 1. Describe the graph when it's between 0 and 1. Well, that's when it goes down, and then to the right, it goes towards 0. Again, it'll never hit 0 over here either, but there's an asymptote there. All right, so it's got questions there you can look at. Page 2. This lesson's longer than the last one. All right, let's talk about the bases and how that affects what the graph would look like and what we're looking at with these exponential equations.
Today I'm going to show you how to use the properties of exponents to interpret exponential functions. In this particular set of examples, I'm going to be referring to the value of boats. I have boat 1, 2, and 3. So beginning with boat 1, the very first number you're going to see is 5,000. This is the initial value of the boat. The next thing you're going to notice is being multiplied by 1.25. This is our percent of change. What is happening to that initial value? And then our exponent of x is where we would put our numbers of years. So if I wanted to know how much his boat would be worth in 10 years, I would replace his x with 10 and then evaluate this. So what else can I tell about boat 1? Well, we know, like we said, the initial value was 5,000, but it's being multiplied by 1.25. What does that tell us in terms of percentage? The number is greater than 1, so it is keeping its value, but it is gaining 25% in value. So if I were to classify this, I would say that it is increasing. So boat number 1 actually is increasing its value year after year by 25%. Now looking at boat 2, same thing. Notice we have the initial value first. It is a value of $4,000. Here our percent is 0.40, our percent of change, and we have the x for our number of years. Now the difference between these two, you'll see, is that this one is greater than 1 and boat 2 is less than 1. So what does that mean? It means that we're going to keep 40% of our initial value. So we know our percentages go up to 100. So if I keep 40, that's also saying that I lost 60. So if I'm classifying this one, I would say it's decreasing. I'm actually losing 60% of the value because I'm keeping 40%. So when I'm looking at boat 3, I have it just in words, but not in the expression. So how can we make that happen? Here we have an initial value of 4,500, the same as we have with boats 1 and 2 at our initial value. Then we're multiplying by our percent of change. So here it says it's losing 50% each year. So if we are losing 50%, that means we are keeping 50%, expressed as 0.50. And then the last thing we add is our x, which is our number of years. So we can easily determine by the way it is written here, our percent of change is less than 1, so we know it's decreasing. And of course, our problem actually says it loses. So we would say it is decreasing. Now, when you look at these two, we have 4,000 times 0.40 and 4,500 times 0.50. A lot of times we tend to think, oh, well, this is decreasing by a lot less because it is 0.40. But really, notice we are keeping 40%, meaning that we are losing 60%, as opposed to here, we are losing 50%. So if you were comparing these two boats, this one is losing value at a much faster rate than boat number 3. So knowing what these numbers mean and knowing how to classify them as increasing and decreasing be very helpful in interpreting these functions. And that is how you use the properties of exponents to interpret exponential functions.
That's a good video to illustrate how the base really affects what's going on, understanding what that base is telling us. Let's talk about key features of exponential graphs here. Key features. So it's important to know key features of different functions as to comparing their graphs. We do that with all kinds of graphs. We do that with quadratics and many different types of graphs. So the y-intercept is always a key feature. Where does this cross the y-axis? That's true for any functions we compare. We always want to know where does it, where is it equal when x is 0? Most of the time, what we're seeing, it doesn't matter what the base is. 1 is our y-intercept. Now that can change if we do some translations with it. Like this shows if p is positive. So this is the coefficient that's out front. So we probably ought to put this in our notes here. P is positive, B isn't. Okay, let me switch over to our notes. Okay, so making this in our notes then, we're going to make a copy of this. if we have the equation a equals p is our coefficient of our exponential equation, b to the x plus k. We're going to just put a k out there, which would be a constant plus 1, -2, whatever the k is. If p is positive, this coefficient, and it may be 1, like here, 5x, amount equals 5 to the x. P is 1, right? We don't have a P out there, so it's assumed to be a 1. And K is a 0 on this one because we didn't put anything for there. So this is just 5 to the x. In that case, P is greater than 0 because it's just 1. It's a positive number. Our base is greater than 1 because in this case we see it's 5. So we expect the graph to look like this, and asymptote at K. Well, for this one, it'd be down on the x-axis, it'd be y equals 0. But the asymptote, I'm just putting whatever k is the asymptote. If there's a constant at the end of our equation, that is going to be the asymptote that it approaches as it goes towards negative infinity. If our base is less than 1, but p is positive, so maybe we have a equals 0.5 to the x, and maybe it's plus 1. Again, we don't have a coefficient out front, so p must be 1. Our base is less than 1, it's 0.5. 1 is our k, so this would be a 1 right here, and it would be going down, decreasing. As x gets larger, this was decreasing close to that asymptote of k. So that's a good illustration for positive p. Now we also have in our notes, it'll show when p is a negative, so we'll add that in our notes as well. So p is less than 0 or a negative number. That could be something simple as a equals -3 to the x. In that case, p is -1. All right, we got a coefficient of -1 out front. All we know is there's a negative, whatever it is. There's a negative. P is a negative. If, again, b is greater than 1, which this is, it's a 3. We're like, well, that's not greater than 1 because it's -3. Well, no, this is really considered the coefficient out front. It's the p. But this is not a decimal number, what we're saying. It's not like 0.3. It's a number that's bigger than a 1, even though it's negative. Then our graph, again, could have a k. But what we're going to see is this graph is going to go down. Again, we'll never get to that asymptote, but it'll get closer and closer and closer as it goes towards negative infinity. And the other case we have, our base is less than 1. So it's a, negative 0.7 to the x. And it could be a -1. K could be a negative number. Doesn't matter. But we're talking about a negative p and a base less than 1. In that case, when we draw our graph, let's change it up and just put a k that's down here. In this case, k is -1. What we would see there, getting closer and closer to that asymptote, but it would go down. As we have a base that's less than 1. It's a fraction. It's a decimal. It's a point something. So when we have a positive, whatever, this is a positive, whatever, 0.5, it's 5, whatever the number is, If the base is a number that's not less than 1, it's going to go up and approach the asymptote going left of whatever k is. If this is a decimal number, 0.5, it's going to go down as it goes towards infinity, closer to that asymptote, again, whatever k is. If this is a negative out front, -3, -0.7, whatever it is, if it's a 3, not something less than 1, it'll go down, again, approaching the asymptote towards negative infinity. With a less than 1, it's a fraction number. It approaches that asymptote going towards infinity. So that's the little cheat sheet to know how these things will graph. Little cheat sheet to have in our notes. And again, it has that right here on this page. So you can copy this down and print this page if you want. It says, describe the y-intercept and end behavior of the following graph. Okay, well, the y-intercept is at -1. And what's the end behavior? As x goes towards negative infinity, the left end goes towards infinity. It just goes up forever. On the right side, as x approaches infinity, y approaches -2. -2, it looks like it'll never touch it, but that's the asymptote. Y approaches -2 as x approaches infinity. Let's see how they say that. The y-intercept 0, 1. The graph starts up on the left. Okay, you could just say that instead of negative infinity, infinity. Up on the left and decays downward and gets close to y equals -2 on the right. So as it goes right, it gets closer and closer to -2. You can say it as simple as that. How about the average rate of change? The average rate of change is the amount of range values change over a given interval. Like a positive rate of change means the graph is increasing, and a negative means it's decreasing. So it says if you think of slope as the average rate of change, Juan's got a job that pays $9 an hour. Y equals 9x. If he works 14 hours, he makes $126 because 9 times 14 is $126. Its average rate of change would be 9 because every time he works an hour, gains 9. Every time he works an hour, gains 9. If we look at this, think about a skier going down this mountain. The skier's decrease in altitude, whatever height they're at, divided by the horizontal distance they've traveled would be the average steepness of this mountain. Because the elevation would be decreasing, the average rate of change would be a negative number. Notice the mountain doesn't make a straight line. Like the amount that it's going down right here is much steeper than the amount it's going down here. But the average would be the average from one end to the other. Oh, I like this one. If we look at this trip, Marisol went from Tampa to Gainesville. And it took 2.5 hours and went 140 miles. So we can calculate the average rate of change for 2.5 hours at 140 miles. I think it's like 56 miles an hour. Yeah, 56 miles an hour. But interestingly enough, Marisol was never traveling at 56 miles an hour because in the first hour, we made it 70. She was driving 70 miles an hour for the first hour. And then in the next hour, only went from 70 miles to about 88. So it went like 18 miles an hour. It must have stopped for fuel and lunch or something. And then the last half hour was again traveling about, yeah, it looks like she was going like 50 miles an hour and half. She's going like 100 miles an hour. She's really speeding. So because the last, well, that may be a little more than half an hour, but the average rate of change is different than the actual rates in place. So that when we look at the average rate of change, we say, what is the average rate of change from -2 to 2? Well, what is it at -2? It is, well, let's put that point in there. -2, comma, 0.1111. There is the point at -2. At +2, it's 9. So if we wanted to know the average rate of change, we're talking about the line that goes, let's see. Not quite. That's close. Really close. Trying to get the the line that goes from this point to that point. That's really what I'm looking for. 0.11111 is less than x is less than 2. Oh, no, I went -2. -2. So I want to know what the slope is on that blue line. If I want the average rate of change, I just want to know from -2 to 2, what is the average rate of change? I don't want to know the slope here and here and here and here and here. It's really steep here. It's not steep back here. But the average would be from here to here. So that's what we talk about when we know the average rate of change. If we want to know the average rate of change from 0 to 2, I want to know the average rate of change. Let's see. Let's see, 0. I want to know right there. What is the slope of that blue? I don't care about the red line. I want to know what's the slope of that line. That's the average rate of change. In this case, it goes one. Oh, let's take off the little half. I don't like the minors. It goes up 1, 2, 3, 4, 5, 6, 7, 8, and goes right to 8 over 2. So the average rate of change is 4. The slope is 4 between 0 and 2. That's the average rate of change, 4. Now the slope is not 4 anywhere along here. This is less than 4. This is greater than 4. It might be 4 somewhere right around here just for one instant. But the average is a lot larger numbers and smaller numbers, but the average is 4. That's what they mean by average rate of change. All right, let's look at page 3. Up to this point, you've only worked with the generic form, b to the x. But what happens if we have an x minus h and a k? Well, here's that k we was talking about. If we add a number on the end, now it's plus 1. So the asymptote went here. Could be a negative number. That's going to be k. Let's see, what's the coefficient? Okay, there's a coefficient of 1. So we got an asymptote at 0. But if we change that k, we can make it go up. See, now it's 1 plus k is 1. If it's 2, changes where the asymptote is. If it's a negative, -2.5, -2. There's also this minus h, just like we did with quadratics, just like we've done with lots of other functions. If we add or subtract the number to the h, it moves it left and right. Look at this. So it moves it left and right, depending on what h is. And if h is a positive number, it's x minus 2. See, h is 2. It moved right, but it's minus 2 in the equation. If it's plus 2 in the equation, it moves left, x plus 2. So this is transformations of the graph. So let's see, 1/3 to the x. If we graph 1/3 to the x, let's just show some examples. You have to be sure to put 1/3 in parentheses, equals 1/3. 1/3 raised to the x. Now that's less than 1, so that's why it's decreasing on the graph. So say when you graph that, make sure you put 1/3 in there. Let's graph that at the same time as y equals 3 to the x. There's 1/3 to the x. There's 3 to the x. These are inverses of each other. Well, not inverses, because the inverse would be over y equals x. But I mean, these are exact opposites. You put them on top of each other. They make a reflection over the y-axis of each other. 1/3 and 3. Example 2. 2 to the x plus 1. That's a good one to look at. So if we did y equals 2 to the x, and then we did y equals 2 to the x plus 1. I didn't do 2, I did x. 2 to the x plus 1. See what I did? X plus 1 moved it left. So instead of being over here at 1, 2, it's at 0, 2. If I get on this, there it is, 0, 2. This point, instead of being at 0, 1, moved over here to negative 1, 1. Everything moved over. Oh, can't get it right on it, but it's right. Yeah, there you go. Everything moved left 1. If this is a minus 1, it's going to move right 1. And then again, if we add a number in the end, it changes the asymptote. See, plus 2 raises up 2. See, this line moved up here from down there. So that's just transformations. Plus 1, minus 2. So this just shows you, here's an example of each shift. You move left, you can move right, you move up, you move down. Just like the transformations we've done with all the other functions. All right, page 4. See if there's anything new here. We're about to run out of time. And fitting functions to data, we've kind of looked at that. But this is a cool thing. It says, okay, if we want -5 to equal -1, that'd be right there. -5, -1. -2, -1. 0, -2. 1, -3. This is a fun one to play with. 2, -5. Can we come up with an equation that would go through those points as close as we can? Well, let's see. If we look at our notes, to make a graph like that, b has to be greater than 1 and p has to be negative. So p is the number out front, which I think is the A for them. B is the base. It has to be a positive number, like 1 or larger. I'll make it -1. Oh, -4. We need to go down. Our horizontal asymptote, okay, should be -1. Oh, that's pretty close. We got a base of 2. We have a -1 coefficient. We didn't need to move left or right. So h stayed 0 and k is -1. And we can't hit exactly that point there because it's straight over. They're both -1. So that's probably about as close as we get. Trying to make it fit. It fits 4 points out of the 5. That's pretty good. See how they do. Oh, they did 2, -2, -1, and -1. And they ended up with the same graph. So there's different answers because we did -1 and 0. All right, here's the lesson summary. An exponential function is functions with the variables and the exponent. Open the software of your choice, set up the coordinate plane, use the grid and axis, enter the equation 3 to the x. It looks like this. The things you look at is the end behavior, the y-intercept, and the average rate of change. And we try to get a best fit. This was a best fit. It's not exact because it didn't get B, but that's the best fit. There's some practice problems here on page 5 and 6. Which function would be the best fit for this data? You may want to graph that. See, 2x plus 1 plus 1, 2 to the x plus 1 minus 1, 2 to the x minus 1 plus 1. Which one would get through these points? You may want to put these points on Desmos, 1, 2. Remember, you can do that just by typing them in parentheses, 1, 2, and then label it. See, there's the point 1, 2. So you can put those points on Desmos. There's 2 there. Page 6. Practice. Graph this, 4 to the x, and then see if it looks like this. There's 6 of these. Graph 1/5 x. See if it looks like that. So it's got just one for the practice graphing. Let's see what our assignment says. Which one is the graph of -4, 2 to the x? There's 4 to choose from. Given the function 2 to the x, which shows that function plus 1, where you add a k of plus 1. Okay? Which describes the key features, which tells you the y-intercept, what it does on the left, what it does on the right of this graph. And you can just go graph that on Desmos. Use this graph. What's the rate of change from x equals 2 right there to x equals 6 right there? If you drew a straight line, what would the slope be? Which exponential function is this? 3, 10, 4, 16, 5, 28. I would graph these points, and see which of these 4 goes through those 3 points. Best fit. That's it. That's it for this week. Graphing and solving when they don't have the same base using logarithms. So we'll have one lesson next week, which will be a video because I will not be here in person. So get that one done next week. The week after that, we have a final, which you can be exempt from. Remember, the final is going to be on Thursday at 9:15, was it? 9:15, a little later than our normal starting time. But that'll be on finals week on that Thursday, unless you're exempt, which I hope you're exempt. There's a lot of folks in here that should be, because you haven't had a lot of absences, missing assignments, grade of 75, all that good stuff. So, all right, guys, have a great week. I will be here on Thursday, but Friday's an A day, so